So, good afternoon, everyone. Hope you all are doing well. So, I thought always it's me who is solving the problems, right? So, let's make today's session a little problem solving sort of session so that it also shows that you're properly working with the problem, and I also get an idea. And if you get stuck, we can go through the problem together, okay? So, since there is one circuit, I'll show you. So this is the circuit. Is the circuit visible to everyone? So basically what you have to do is, first of all, you people solve the circuit and find out uh, the expression for gain, that is V out by V in. Because there are 4 to 5 consecutive problems which are based on this particular circuit only. So I want you people to solve this particular circuit and let me know what is the expression for gain, that is V out by V in, that you are getting. So it's 3:09 now. So maybe 5 minutes. Let's see who all can solve it till 3:15. And if you get stuck somewhere, please feel free to ask. Okay, so you people try to solve this particular circuit and let me know the expression for V out by V in. Okay, so you have time till 3:15. So you people can start solving. Since we are going for AC analysis, so this will you have to perform small signal analysis and let me know the small signal gain. Okay. So you people try till 3:50 and let me know.
Ma'am, RD must be above now.
So I asked you to let me know the AC gain expression. So V out by V in for
But
this
RD
particular
must be above
circuit.
now.
Sorry. In terms
RD,
in
RD
terms
must
of
be above.
R1, R2, R3, R1, R2, RS, and RD.
Okay.
Yeah. In variable form only. You just let me know the expressions. Then we'll move forward. Why I am asking you this is because there are 4 consecutive questions which are based on this particular circuit. So first, if we handle this particular circuit or solve this particular circuit, then we can move ahead. That's the reason. Okay. Abhijit, you have raised your hand. Is there any issue?
Ma'am, the gain is minus GMRD upon 1 plus GM. Is it correct?
Sorry, come again.
We, gain is
Uh-huh.
minus GM into RD divided by 1 plus GM.
No, you are missing something. You might try again. Almost it is correct. There is one RS which should come in your game that is missing. So try to look into it.
Yes, ma'am. In denominator it is 1 plus GM RS.
Okay, you got it.
Yes.
Let others solve. So we have 3 minutes more. And then if everybody gets it, then it's fine, or otherwise I'll quickly go through, then we can move ahead. Abhishek, maybe you can solve this question, the first question. You have to find the value of RS. Maybe you can go ahead and solve.
Is it GM into RS parallel with RD?
Uh, GM into RS parallel with RD.
Yeah.
So it's GM RS parallel with RD. This is what you said, right?
Yes, yes.
Okay. No. No. Sorry, this is not correct. So basically, the answer is, I'll reveal the answer. So please let me know who all have got this answer correct, okay? GM into RD upon 1 plus GM RS. This is the final expression that you will get. So how many of you have got this answer? This is the expression for gain, and if we try to reduce it, so we know like GMRS is greater than 1, so we can reduce it to minus RD upon RS. So this is what that you'll get. So may I know how many of you have got the answer correct? So maybe you people can raise your hands. Yeah, Abhijit, I know you got it right. Other than Abhijit, anyone else?
मैम कौन सा टॉपिक हो रहा है?
Sorry? आप कुछ बोल रहे थे, आपकी आवाज़ नहीं आई. हेलो हेलो. So do you want me to go through this gain expression and solve this? Students, am I audible?
Yes, ma'am.
So would
Yes,
you
ma'am.
like me to solve this expression for gain?
Yes, ma'am.
Okay, so let's quickly go through. So first of all, you see that this is a PMOS, right? This is clear to everyone, right? So let's quickly make the small signal circuit and solve this. So how will the small signal look like? Source, gate. So first of all, any doubts in the small signal? the small signal equivalent circuit. Do you have any doubts? Is the small signal clear to everyone? See, if you people won't acknowledge,
Yes,
Yes,
ma'am.
ma'am.
then I'll take it as yes, okay? If your people face any issues, please raise your hand, or you can just unmute yourself and ask, okay? Or otherwise, I'll move ahead. Okay. So the small signal is clear to everyone, no? So here we are providing Vn, and here we'll take V out, right? So if we see what is the value for VSG, Vs minus Vg, right? And here Vs will remain, let for now, let Vs be Vs, and Vn is, sorry, Vg is Vn. This is VSG. Now here if you see in this particular part, we can see that these are connected actually. RS to this dependent current source to this resistor, and this is ground again. So this is a complete path, right? So now let's handle this complete path. So if we see here, what is the expression for V out? It is GMP VSG into RD. We know? Yeah, Sanjay, what's the issue?
Yes, ma'am. Yeah, so output impedance of MOSFET RDS will be also there, right? Between source and drain.
Uh, if you want, you can consider, but here it was not mentioned, so I have simply neglected it.
Okay.
Okay? Since nothing
Yeah.
was mentioned here, so to make it very simple, I have simply neglected it.
Yeah. Okay.
Okay? Yeah. So here GMP Vs minus Vn. So everywhere we can see that this Vs is actually an issue. So if we want to write the expression for Vs, what will be Vs? Vs actually if we see clearly, so this is Vs, right? The drop across Rs. And since a single current is flowing through this dotted path, so can we write it as this? So here I would like to know how many of you got this expression. Like, how did I come to this conclusion? Is it clear? The expression for
Ye-
Vs, is it clear?
Yes, ma'am.
Yes,
This is
ma'am.
Current is reversed and
yeah,
it
so
was.
that's why this minus is coming into picture, and since it is a single path, so single current will flow.
Yes,
This is
ma'am.
clear, right? Okay,
Yeah.
now we can solve it. Vs remains Vs, Vg becomes Vn, Rs, if you solve you'll get Vs as GMVN Rs upon 1 plus GMRs, right? And we'll substitute this in the expression 1. So we'll get GMP into GMVNRS upon 1 plus GMRS minus Vn into RD. So we got the gain. This is clear to everyone? Is this clear? Any doubts?
Yes, ma'am.
Yeah, yes, ma'am.
This is clear, no? So we have got the gain, and the gain turns out to be minus RD by RS. Okay? So we have tried to solve the circuit. Now let's look into the question. Okay? So this is the question. So here it is given that the current through the potential divider R1 R2 is 0.5 microamperes. So current flowing through this is 0.5 microamps. Current through MOS device is 124 microamps. So since it is flowing through MOS device means it will flow throughout this line, right? Throughout this path. And this current is 124 microamps. Okay. And the approximate gain is minus 5. So approximate gain matlab this is the actual gain, right? This is actual gain. So approximated gain means this one. We have approximated it, right? Considering GMRS to be much greater than 1. So we'll apply it here. So the third condition is RD by RS is 5. Okay? And the output can swing symmetrically over the largest possible range while maintaining the device in saturation. Okay? So the first question is we have to find the value of RS, and it should be in kilo ohms. So we have to get the value for this. Okay? So I guess Abhijit, did you try this one? Abhijit, could you get the value for RS? Hello, are you there? I don't know. Okay, let's move ahead and let's see. So first of all, what are the things that we got? RD by RS is 5. So RD is 5 times RS. This is one thing that we got. Yeah, Vicky. Any concerns? Okay. Yeah, Vicky, go ahead. Do you have any concerns? Okay. So,
Hello,
yes.
ma'am. Actually, I got two equations, but
Uh-huh.
cannot find values of resistance from them.
Okay, so can you let me know, like, let us all know what are the expressions that you got?
Ma'am, from first condition,
Mm-hmm.
the the resistors R1 plus R2 is 10 mega ohms, and
Yeah.
from MOSFET current equation,
Mm.
ID is equal to K VAG minus VT bracket square.
Yes,
I
yes.
got source to get voltage VAG equal to 0.679 volts, and we can
0.679.
use that equation.
Mm-hmm.
Uh, but
So,
I'm getting one equation and two variables. That's why I
okay, okay.
cannot proceed further.
So, first of all, we cannot use that R1 plus R2 ka expression here, right? Because we have to find the value of RS. So, this, that expression is eliminated. So, let me solve it this way. So, here you can see that gain is negative. Can you see that gain is negative? That means as we increase Vn, the current actually reduces. This is because gain is opposite, no? So it's like if this is your input, So your output will look like this, V out. So if you see clearly, as we are trying to increase our input, our output reduces. And as we try to reduce our input, our output increases. Okay? You can see it clearly from here. The similar thing happens with current also. That is because our output here in this case is actually 5 minus ID RD minus VDS. In this particular circuit, if we see, so V out is actually ID into RS, or it can be written as 5 minus IDRS into VDS, right? Sorry, minus VDS. So we can write it either ways. So here we can see that V out is actually proportional to ID. So it will also follow the same trend. So as we try to increase the input, the output reduces. So this trend will be followed by current as well. So if let's say I say my DC current to be IDC and AC current to be small id, and let's say my total current be I total. So this will be summation of DC plus AC. So we know once the bias point is fixed, our IDC will be fixed. So the changing current will be ID. So there is a chance that our VG is increasing or Vn is increasing such that this ID, that is AC current, it actually nullifies our DC current. So in that case it will be IDC minus IDC, that is 0 will be our I total. That is one case. Another case in which Vn, we are reducing Vn such that our ID becomes equal to IDC. So in that case our I total will be 2 IDC. Is this clear? So since it is an AC signal, so if this thing is IDC, so this will be minus IDC, right? So think of it in this manner. And this is the DC bias point. Okay? So for the condition when I total becomes twice of IDC, at that time Vn is actually very low. So the lowest Vn kitna ho sakta hai? It should be like your MOSFET should be turned on, no? So MOSFET should be turned on, and your VGS minus VT will actually be equal to VDS. Okay? Is this clear? So we know that ID equal to K, sorry here VSG hai na, VSG hi likhte hain. So we don't get confused since it is a PMOS. So VSG minus VT whole square. So what I am saying is twice of IDC equal to K VSG minus VT whole square. So from here we get VSG minus VT to be square root 2 IDC by K. Okay, and for this to be minimum, and for our MOSFET to be in saturation, this is the minimum condition that needs to be followed, right? So this is actually equal to VSD. Now if I try and write the expression for VSD, VSD is how much? 5 minus ID RS plus RD, right? This is clear? VSD ऐसे इतना कैसे आया? See, when we
Yes, yes,
Yes,
ma'am.
ma'am.
this is clear, right? So ये वाले expression को we have simply modified it और कुछ नहीं किया. Now इस expression में you know VSD, so you simply substitute. Yeah. So you simply substitute this equal to 5 minus ID RS plus RD. We don't know RD, but we know RD in terms of RS, right? How much was it?
5 times
5
R
times RS, right?
RS, yes.
So यहाँ पे we know IDC, we know K, so the only variable is RS. So can you quickly solve and let me know what is the value for RS that you are getting in kilo ohms? Or maybe you can solve this. I'll simply write it down. It is 3.189 kilo ohms. Okay? Maybe you can solve and check if you are getting this correct or not. Okay? RS is 3.189. Now what is the expression for, what will be the value for RD? How much is RD? It is simply 5 times RS.
5 times
So
RS.
we'll multiply it with RS and we'll get it somewhat around 15946. Okay? Now next question. So what is the value for R1? So how will we find R1? So what will be the thought process for finding the value of R1? So it was given, yeah, it was given that current through R1 and R2 to be how much? 0.5 microampere, right? This was the current. Yeah, so this was the current. So R1 plus R2 into, let's say, I dash equal to 5 volts. So R1 plus R2 is 5 by 0.5. So R1 plus R2 is 10 mega ohms. Now next thing is, okay, this is known. We know IDC, current we know. Now when we know IDC, it is K VSG minus VT whole square. So VSG is VT. So VSG we can find out from here. We can solve and find out the value that you are getting. And Vs minus Vg, so it can be written as 5 minus IDRS. So question number 3. Value of current was okay. So what is the value that you are getting? VSG कितना आ रहा है इसमें for this expression? You can calculate simply ना. यहाँ पे VT is 0.5 volts. IDC you substitute. IDC 124 microvision, right? K is also given. K is, yeah, it's 3.83 millisiemens. So after substituting these values, you'll get VSD. And then for Vs, it can be written as 5 minus IDRS minus VSD. VSD will be how much? VSD minus VT is equal to VSD. If we substitute this, so from here you will find Vs, you have to substitute it here, and then you will get the value for Vg. So Vg turns out to be 3.94 volts now. ये clear है ना? Is this clear to everyone?
Yes, ma'am.
This expression we
Yes.
used it earlier also, no? So we are simply doing the same thing. And यहाँ से we are trying to find out the value for Vs, and then we are substituting it to get the value for Vg. Now once we got Vg, then what we'll do? So Vg is equal to R2 into R1 plus R2, right? So from here we know R1 plus R2, it is 10 mega ohms. VDD is known 5 volts. Vg is known from above expression, so we can simply find R2, right?
Yes,
So
ma'am.
once we know R2, then we also know R1, right? 10 mega ohms minus R2 कर देंगे तो R1 आ जाएगा ना? So that's how we'll find R1 and R2. So these questions are like, third question is find the value for R1, and fourth question is find the value for R2. So we have to simply do those calculations. So that's why I asked you people to solve that circuit first. So 4 questions were connected to that first circuit only. Clear? Now let's move on to next question. So here in this question, it says that PMOS, it has a lambda of 0.05 per volt. GMB is 1 by 5 times of GM. So I would like to ask, how many of you know what is GMB? Do you know?
It's the body effect.
Yeah, it comes because of body effect. So do you know how we calculate this, and what is this majorly, how we evaluate this GMB?
Ma'am, if a body is moving with source, then it comes and be applied Taylor series. Actually we take BSG, BSD, and VSB. ID equals to function of this, and then we
Yes.
apply Taylor series to it, and then we find GM.
Yeah. So I'll simply show you the derivation for GMB, a basic derivation to give you a brief idea how GMB comes into picture. Okay. So we always have use this practice, that is we basically try to sort like we short body with the source. This is the basic idea, so that VSB turns out to be 0. But this is not true always. This is not true always. And if you would have made like layouts and stuff, so you can see that there is a body terminal at very end of your whole IC. So there are chances that there might not be a short between source and body, and sometimes we intentionally don't short source and body, and we want to basically use it for our advantage, as this also affects the VTH, that is threshold voltage of the device, as well as other factors come into picture. So even in current, so if we say our output resistance is like infinite, resistance is infinite, or GDS is 0, then we are basically nullifying the effect of, so ID becomes independent of VDS, right? But when we say there are short channel effects coming into picture, we say that earlier ID was only function of VGS in saturation. I'm talking particularly in saturation. But when small channel effects come into picture, so ID becomes a function of VGS and VDS. But when this thing comes into picture, that Vs is not equal to Vb, in that case ID actually becomes a function of VGS, VDS and VBS. Okay, so if we talk about universal current equation, so we write it like Gm VGS plus GDS VDS plus GMB VBS. This is what universal current equation looks like for a MOSFET with body effects. So we want to talk about this GMB, how it comes into picture and how it basically looks like. So let me show you a brief derivation of how this comes into picture and what is its like what is its values, like what are its values and which range it turns out, and we'll talk about all these steps in this. So GMB, we can say body conductance. People address it differently, but G, we know it is conductance, and since it is due to body, we can simply say it as body conductance as one of the terms. And if we see, the conductance is basically the change in current with respect to change in voltage, right? So it's ID by voltage. Which voltage? Change in body voltage. So it is Vp. Okay, this is GMP. So we can write it like, we can write it this way, mathematically. And if I talk about a MOSFET, so let's draw MOSFET first. I'm drawing an NMOS. Let's say this is VC, that is V channel. Outside, and this is VB. So if we see, here there is VG and here there is VB. So these voltages are coming in series and it appears like a voltage divider circuit, right? So if I write, I can write it this way, no? So I'm further bifurcating this. Now what I'm saying as voltage divider, so here it is not voltage divider made up of resistors, but it is a voltage divider made up of actually capacitors. So, oh, if I be very particular, so this, so actually this voltage, yeah, so I'm talking about this voltage actually, the surface potential, I'm talking it, calling it as VC. Okay, so if we look into this thing, so it looks like this is a capacitor which is actually due to this oxide capacitance. This is VG. There is another capacitance coming into picture, which is because of this channel formation, and here we have actually a depletion capacitance. Due to depleted charges and channel formation, we have a depletion capacitance, and here we have VB. And as I said, VC is actually the surface potential, so it will come in between Cox and CD. This is clear? This is clear, right? Now let's say we want to get Vg by Vc. So in that case, what we'll do, we'll simply put Vg to ground. Here it was Vb, and we'll put Vb to ground. If we see, Vc is actually equal to Vg into 1 by Cd upon 1 by Cx plus 1 by Cd is equal to Vg upon 1 by Cd plus Cx. And this is known as M. This is a very famous factor known as gate control factor. Ideally it should have been 1, but practically it's not. Ideally it should be 1, but practically it's not equal to 1, since we have CD by Cox and it's never 0, right? So if we want Vg by Vc, so we'll simply have CD plus Cox by Cox. So this is 1. Now next thing what we want in this expression, we have got this one. What is ID by Vg? Yes, what is ID by Vg?
GM.
Yes, it is Gm, no? So it's like Gm into Vg by Vc into Vc by Vb. So now we are going for Vc by Vb. So when we are going for Vc by Vb, so then we don't need any Vg, right? So we'll put Vg to ground. Okay. And then we'll calculate. So here we'll get Vc equal to Vb 1 by Cx 1 by Cx plus 1 by Cd. So Vc by Vb is actually Cd by Cd plus Cx 2. So GMB is ID by Vb, that is ID by Vg into Vg by Vc into Vc by Vb. This is Gm. This is Cd plus Cox by Cox, and this is equal to Cd upon Cd plus Cox. So if we cancel this, we are left with Gm into Cd by Cox. This is ID by Vb or GMB. So can we write Cd by Cox in some other terms? Can we write Cd by Cox in some other terms?
Yes, gate control.
Yeah, right. So I just mentioned gate control factor, right? So here this one is gate control factor M. So M is actually 1 plus Cd by Cox. So Cd by Cox will be m minus 1, right? So here we'll substitute m minus 1. This is GMB. Now if we look clearly, we know GM is in some millisiemens, right? Generally talking, in general sense, we have GM in few millisiemens. GD we have close to few microsiemens, okay? But if you look clearly, GMB is also in millisiemens, as it is GM times m minus 1. So if we see, the effect due to GMB is higher than GD. Can we see this clearly? Are you able to imagine this?
Yes, ma'am.
So basically, the effect due to internal output resistance or second order effects, GD comes out due to second order effects, right? Like when we have short channel effects, we see GD coming into picture. And this GMB comes because of mismatch between VB and VS. So we can clearly see that the effect caused by mismatch between VBS is higher compared to our second order effects, right? So this is the conclusion that we can draw from these conductance values. So is the conclusion clear?
Ma'am, GT is due to channel length modulation or short channel effect.
Short channel effect में ही we say channel length modulation is one of the second order effects, no? Short channel effects में.
Okay.
Yeah. Like we have Dibble and other stuff also, but like channel length modulation is also due to this thing only. Like it's also a second order effect. And basically what I mean, by second order effects is ideally ID by VDS in saturation, it should turn out to be like this, right? It should be flat. There should not be any slope. But due
Yes, ma'am.
to second order effects, what happens after this, it turns out like there is a slope. So we want constant current source, MOSFET to behave as a constant current source. But what happens is, due to these effects, like second order effects, like short channel effects, all those things, let's say Dibble and channel length modulation, because of all these effects, we see this slope coming into picture. And this is actually detrimental in our case. So basically we wanted our MOSFET to behave as an ideal current source, like constant current source, but it doesn't behave that way. So this gives rise to our GDS factor. The slope actually gives rise to GDS factor. If it was like this, no. तो क्या होता है? Here you can see there is DID by DVDS is actually 0. इसका मतलब GDS is actually 0.
Yes, ma'am.
So ये slope की वजह से we get this GDS factor. और GMB जब हम बोलते हैं तो this comes because of the voltage mismatch between body and source terminal. Got it?
Yes, ma'am.
So what I want to say is, see here, GMB is not very small factor. Like GDS is in few microsiemens, but if we see clearly, this is close to 1.1. M is almost close to 1.1 in most of the cases. So when it happens that way, so GM is actually GMB is actually 0.1 times of GM. This is not very small, right? Compared to GD, it is this is quite high. So that's why
Yes, ma'am.
that's what I basically wanted to highlight, that the effect of GMB is higher compared to GD. So if we say in terms of values, it will be like GM, then GB, then GDS. So this is the conductance sequence that a MOSFET will follow, and that is this is almost applicable to all types of FETs. So this is what I wanted to highlight. So could you understand this? Any doubts? Is this derivation clear?
Yes, ma'am.
This derivation is clear, right? So okay, it's already 4 in my clock. So let's not go further. If you have any questions in previous, whatever we solved previously, you can ask. So first of all, there are few derivations we did today, right? So first question, first derivation for gain. Is this clear to everyone? Does anyone have any doubt in this particular derivation?
No, ma'am.
No, right? Please feel free. It's okay if you don't understand, okay? See, facing afterwards, like if you face these type of questions and there you are unable to solve, it's more critical in that case, no? Here at least you have someone, I can help you out with this. So feel free to ask.
My ma'am,
Yes.
somewhere I feel stuck in drawing a small signal model of different like NMOS and PMOS.
Okay.
Where should I write S and B and things like that?
Yeah,
So
yeah. Good thing you asked. See, so I'll take a fresh page maybe. Yeah. So here, small signal model, when we are drawing small signal model, so this is an NMOS. For NMOS, what is, so you understand that wherever we show this current direction, this is basically a source terminal. You understand this, right?
yes, yes, ma'am.
Okay. So if it is a PMOS, we will have it like this. So this is source, drain and gate. Now for NMOS, so we know generally source is at lower potential than drain. Is this clear? For an
Yes, ma'am.
NMOS, source is at
Yes,
lower potential than drain. So we'll draw source at the lower end, drain and gate at upper ends, higher ends. And here it will be a source. Okay, this is clear.
yes, yes, ma'am.
And now we know that gate, there is an isolation between gate and like body of the MOSFET.
Yes,
So VGS के बीच में the resistance is actually infinite because of this insulator. तो यहाँ पे अगर if it would have been a BJT, so यहाँ पे we would have replaced it with a resistor. But since here we have infinite input resistance, so we simply keep it open and it becomes VGS. This is clear?
yes, ma'am.
Okay. Now we have a voltage dependent current source जो कि होता है GM/VGS,
GMBGS.
है ना?
Yes,
इसके
ma'am.
अलावा if there is an output resistance, let's say GDS is not 0, in that case this will be R0. Clear?
Yes,
So this is the basic small signal model for NMOS. Now here see, current is flowing from, current का डायरेक्शन देखो, current is flowing from drain to source.
drain to source.
आपका इसमें करंट का डायरेक्शन क्या होता है? द करंट इज फ्लोइंग एक्चुअली फ्रॉम ड्रेन टू सोर्स. कैन यू सी दिस?
Yes.
सो वी आर फॉलोइंग द सेम कन्वेंशन. क्लियर?
Yes, ma'am.
ओके. नाउ आते हैं पीमॉस में. पीमॉस के केस में व्हाट हैपेंस? सोर्स इज
Source to
एट हायर पोटेंशियल देन ड्रेन.
yes,
तो जो हायर पोटेंशियल में होगा यू विल ड्रॉ इट टुवर्ड्स द टॉप ऑफ योर पेपर, एंड जो लोअर पोटेंशियल में होगा इट विल कम एट द बॉटम ऑफ योर पेपर. मतलब हाई टू लो
yes,
कभी भी फ्लो होता है ना, और करंट कभी भी हाई टू लो ही आप दिखाते हैं. सो
yes, ma'am.
उसी कन्वेंशन में विल ड्रॉ. सो यहाँ पे सोर्स. ना सोर्स को इतना बड़ा क्यों बनाया हमने? because mostly it's like source is the sharing terminal हमारे इस केस में. जब आप एक MOSFET देखते हैं तो उसमें आप पोर्ट्स की अगर बात करते हैं, सो जी एस दिस इज एक्चुअली इनपुट पोर्ट and DS is actually output port. Okay, and here the shared terminal is actually S,
Yes,
जो
sir.
ड्रेन के साथ भी शेयर होता है और गेट के साथ भी. सो दिस इज द रीजन वी ड्रॉ दिस लॉन्ग लाइन फॉर सोर्स. ये क्लियर है?
Yes, sir.
ओके, सो यहाँ पे भी हम लॉन्ग एक सोर्स के लिए लंबी लाइन विल ड्रॉ. एंड इसमें सिंस सोर्स हैज़ हायर पोटेंशियल तो सोर्स ऊपर आएगा. अगेन स्मॉलर गेट एंड ड्रेन. ठीक है. नाउ यहाँ पे कन्वेंशन क्या होता है, वी डोंट से
See.
इन PMOS. For NMOS we have VGS to be greater than 0 in case of NMOS. In case of PMOS, this is for NMOS. For PMOS it is VSG that is greater than 0, right?
Yes, sir.
तो यहाँ पे it will be actually VSG not VGS. ठीक.
Yes, sir.
अब आएंगे डिपेंडेंट करंट सोर्स की बारी. सो दिस विल बी अगेन GM VSG
It's
not
G.
VGS. Okay,
Yes, yes.
and here also we can have R0. Clear?
Yes, ma'am.
Yeah. So here you see यहाँ पे करंट कहाँ से फ्लो हो रहा है, it's flowing from source to drain. And if you look into your like your symbol, circuit symbol, you'll see that in PMOS your current actually flows from source to drain. So वो जो convention होता है it should be met. Okay. और
Yes,
दूसरा
ma'am.
ये ध्यान रखना है लाइक SG और GS. सिमिलरली अगर करंट का भी एक्सप्रेशन लिखते हैं तो GM VGS प्लस GD VDS होता है फॉर NMOS. This is I'm talking about universal current equation for MOSFET. This you can apply anywhere, okay? And for PMOS, it becomes actually GM VSG plus GD BSD. This is for PMOS. Is this clear?
Yes, ma'am.
So this is something we need to keep in mind. Like ये जो S और G का interchange है और S और D का interchange है, और current का flow should be considered. And कौन सा potential high है, low है, उसके हिसाब से we draw this. तो this is for PMOS. ये दोनों समझ में आए?
Yes, ma'am.
NMOS और PMOS का equivalent circuits, small signal equivalents.
Yes, ma'am.
Okay. और कोई concerns?
Ma'am, when we have common drain and common gate, इस टाइप में थोड़ा वो
नहीं देखिए,
प्रॉब्लम.
your MOSFET will be this much. ठीक है.
Yes, yes, ma'am.
इसके बाद क्या करना है, आगे क्या आएंगे, रेजिस्टर्स कनेक्टेड होंगे. सो यू हैव टू सी कि कौन से टर्मिनल से कौन से टर्मिनल के बीच में रेजिस्टर्स कनेक्टेड हैं, उसके हिसाब से यू हैव टू ड्रॉ योर स्मॉल सिग्नल मॉडल. ओके. फॉर
Yes, ma'am.
सपोज हम लोग का हमेशा गेट में यू हैव ऑब्जर्व दैट यू सी दिस रेजिस्टर बायसिंग फॉर गेट,
Yes, ma'am. Yes,
VDD
ma'am.
एंड ग्राउंड, राइट, R1 एंड R2. और स्मॉल सिग्नल में मैंने क्या बताया था कि हम लोग VDD को एक्चुअली DC ग्राउंड मतलब AC ग्राउंड करते हैं, बिकॉज दिस इज़ DC नो.
Yes,
सो AC ग्राउंड होता है, इसका मतलब आइडियली ये भी ग्राउंड है. तो अगर ध्यान से देखेंगे आप तो यहाँ पे गेट टर्मिनल से यू हैव टू रेजिस्टर्स कनेक्टेड टू ग्राउंड. सो व्हाट यू विल सिंपली डू, यू विल सिंपली कनेक्ट टू रेजिस्टर्स, दे विल बी कनेक्टेड टू ग्राउंड. यहाँ पे सिंस सोर्स इज़ ग्राउंडेड तो डायरेक्टली आप सोर्स से शॉर्ट कर सकते हैं, लेकिन समटाइम्स इफ़ देयर इज़ RS लेट्स से, तो इन दिस केस you cannot short it with source because यहाँ S is not connected to ground. उस केस में क्या होगा, you'll see an RS which is connected to ground and here R1 R2 are connected to ground and here you get input. ये clear है?
yes, ma'am.
और इसके बाद क्या एक और क्या कनेक्टेड होता है, मोस्टली RD कनेक्टेड होता है, राइट. सो
Yes.
RD अगर आप ध्यान से देखेंगे so it's connected between drain and AC ground.
Ground. Yes.
So ड्रेन टू ग्राउंड, सो ड्रेन से ग्राउंड के बीच में यू हैव दिस रजिस्टर. सो मोस्टली यही कॉन्फ़िगरेशन होता है ना, जितने भी
Yes,
हम लोग
ma'am.
एम्पलीफायर कॉन्फ़िगरेशंस देखते हैं. सो ऐसे कनेक्ट करना है. फॉर सपोज इफ़ बाई चांस किसी ने ये शॉर्ट किया गेट और ड्रेन को, तो ये रजिस्टर जो आर एक्स है ये कैसे दिखेगा?
Between drain and gate.
तो ये कहाँ पे लगेगा? ये ऐसे लगेगा.
Yes, yes, ma'am. Yes, ma'am.
ठीक है.
Yes.
सो दिस इज़ हाउ वी ड्रॉ. तो मॉसफेट का बेसिक जो स्मॉल सिग्नल है वो यूज़ करेंगे. उसके अलावा बाकी में डीसी ग्राउंड अप्लाई करके रजिस्टर्स को सिंपली अटैच करना है कि कौन से टर्मिनल से रजिस्टर किस टर्मिनल के बीच में कनेक्टेड है, बस और कुछ नहीं करना है. उसके बाद यू विल अप्लाई नॉर्मल KCL KVL एंड यू विल स्टॉप.
Okay, ma'am.
Clear? Any further
Yes.
doubts? Any concerns? Anybody?
Ma'am, which textbook we need to follow for this, for especially problem solving?
For problem solving, you can go ahead with like this level of problems you can find even in Mazari. Mazari's book, you can find these type of problems. Like these type of normal basic problems you can find in Mazari. Sorry,
Rajavi.
Razavi, sorry.
Yes, ma'am.
Yeah, Razavi, it's not Mazari. Professor Mazari's lectures, yeah. Razavi's book, yes. Razavi में you can find all these configuration based जितने भी amplifier based problems जो है ना, based on MOSFETs you can find in Razavi. And is there any other book that you know? So this level of problems are there in Razavi. And for even higher level, there is another book. I'll let you know. Give me a moment. There is this book for analog CMOS IC design. So you can follow that as well. I'll let you know the name. सेशन फिनिश हो गया क्या? ओम, सेशन फिनिश हो गया क्या? एनालॉग सीमोस के बुक का नाम क्या था? वो भी रज़ावी ही था. एनालॉग सीमोस बाय रज़ावी. हाँ, बुक का नाम नहीं याद है. अरे यार ये किसमें है? सीमोस एनालॉग. There is this famous book for analog CMOS IC design. There also you'll find these type of problems, all like folded cascade, and all these types of current mirror circuits, their analysis and stuff. I'm actually trying to figure out the author.
Approximate, ma'am. Microelectronics.
No. Analog CMOS. Yeah. So analog CMOS IC design by Razavi is for higher level, and basics Razavi has this basic microelectronic based book also. So there you'll find like normal problems based on CD, CS, CG, these type of configurations. If you want to go for higher configurations like current mirror circuits, cascode, folded cascodes, and these type of complex circuits, and further moving forward you'll find op amps, OTAs. So these type of circuits, if you want to go ahead and explore. So you can go for analog CMOS IC design, and this is also by Razavi. So yeah. So author is Razavi for both, but it's just that the higher level problems you'll find in design of analog CMOS IC, like analog CMOS integrated circuits, and a normal. There is another Razavi for basic microelectronics one. So there you'll find basic problems on CS, CG, and CD configurations. Yeah, then you can go ahead and explore. Any further concerns? Citra Smith also has few basic level questions like CSCD, CG configurations, like basic configurations you can find in Citra Smith as well. For higher level of configurations, we'll need this CMOS analog CMOS IC design books by Razan.
Okay, ma'am. Thank you.